Thank you so much, Rima, for the very nice introduction. Also, thanks so much for giving me the opportunity to give a talk here. Let me start by sharing my screen. Yeah, so I hope everybody can see this. Okay, yeah, graph convolutional neural networks. I think in general, I mean, we know about the impact of deep learning in public life, various instances, autonomous driving, telecommunication, legal issues, and certainly the whole healthcare sector, which, I mean, unfortunately these days became even more important than it already is. On the other hand, there was just about 2 years ago an incident at one of the big AI conferences where one of the plenary speakers, Ali Achimi, claimed that right now machine learning is at the stage of alchemy, and so there is a huge demand for making it on a theoretical basis more rigorous. Right now, I mean, that's what he claimed. People do a lot of trial and error, test things out, but there are basically no rigorous criteria how, for instance, to choose an AI architecture over another. On the other hand, I mean, we certainly also see spectacular applications. Basically, a year, not even 1 year ago, there was this article about protein folding where there was a huge breakthrough now using these type of approaches, AI, and you see AlphaFold. I mean, what a gigantic leap indeed it is in performance predicting the folding of proteins. I mean, then coming more to the, let's say, mathematical setting, and that is also how I came to this area, because, I mean, Rima said in the beginning that I originally worked on applied harmonic analysis, imaging sciences. This area was, I think, one of the first which was affected by deep learning methods. I think it started around 2012, because in imaging sciences, I mean, you don't have a rigorous model what an image is. So these techniques are very accessible for learning techniques, and one could easily see and quickly see how effective deep neural networks are in that regime. And here are just a couple of tasks which one needs to solve in imaging sciences. Most of them are inverse problem type. And using deep learning, these new type of approaches often easily reach the state of the art. Then the area of partial differential equation was a bit slower. Why? Well, I mean, we have solvers. It's not clear why those are needed, why neural networks are needed in this case. But I mean, whoever attended our workshop last week, I mean, know the effect why neural networks are that effective in this regime. And it's particularly in the high dimensional regime where neural networks are able to circumvent the curse of dimensionality. So it's a very exciting area. There's a lot of research in this direction. And I would like to tell you now a bit about where I view the main theoretical directions. Then we will delve into graph convolutional neural networks, and I will show you concerning one direction some of the progress we made. But I would like to make a short break here, because the idea was that also we introduce ourselves to some extent. And what I would like to do is I would like to show you a little bit about how I build up my career. And then on the next slide, I would like to also pose a couple of recommendations from my viewpoint, what actually helped me in getting where I am right now. And so I hope that maybe for some people who are interested in that and attending this talk, that might be helpful for their career as well. Because, I mean, when I started my career, I wanted to become a high school teacher. I mean, I certainly had no idea that I might end up a professor eventually. So, but then, I mean, I liked mathematics so much, so I switched to studying diploma in mathematics, and then I also liked computer science. So I studied both of that. And meanwhile, I got a position as a TA at a chair. And so then it was actually not my idea to continue with a PhD, but I mean, let's say my supervisor in that sense, I mean, who had this position, he suggested that he would be happy if I would continue as a PhD under his supervision. So there was an opportunity, and then I thought that might be interesting. And so I took that opportunity, and then I got my PhD at the University of Paderborn, it was, I mean, the problem I had was that I wanted to go more into an applied direction, whereas my supervisor was in absolutely pure mathematics. And so sometimes, I mean, doing that PhD was not that satisfying as one would like it to be. And so at the end, I mean, I wasn't sure what to do afterwards. But at a conference, I had met a professor from the US, and I had approached him and asked him if he wanted to be a referee for my PhD thesis, and he agreed. And so through that connection, then he actually offered me to become a visiting assistant professor at Georgia Tech for 1 term. And so I took that opportunity again and used that as a decision to reach a decision what to do with my, well, I mean, how to pursue my career, whether to go to industry or whether to stay in academia. And I liked it that much. I got in contact with a lot of people in the US when I was there. So I decided to continue then as a postdoc. And so then there were in Germany some steps. I had to move to another university because my supervisor retired. I got a fellowship again for staying in the US. I got my habilitation. And then I wanted to again go to the US to also some of the, let's say, top universities. And I then decided to apply for this Heisenberg fellowship, and I contacted people at those universities whether I can visit them, and that worked out. It was, I mean, a great time for me. And so then, I mean, I came back to Germany, I got this position, and then continued in Germany. And at some point, as I already said, when these new methods came up, then I also made the switch in research and moved to AI research. So I think, I mean, if I think about these career steps, from my point of view, I mean, certainly in addition to research, I mean, that's always, let's say, the first. But I think what's also important, I mean, from my perspective, is really to approach people, to talk to people, also to talk to senior people, to extend your network, because that gives you a lot of opportunities. Like I, for instance, was this professor, it was actually Chris Heil from the US, who then invited me for this visiting assistant professorship. So knowing people, also asking them sometimes for advice, I think is a really great idea, and it helps a lot. Also being proactive to advance your career, applying for instance, for a fellowship, and also if one travels, I mean, seeking what I did to go really to, I mean, top universities. And also what I found is, I mean, there are sometimes opportunities coming up which you don't expect. And so I think it's very important to be open to those, and also sometimes take a chance, and even if it's not clear what comes out, but I mean, then let's say embracing opportunities in that way. Also, since right now, I mean, there is so much research out there, I think it's important to show your work. So for instance, when I was a young scientist, I mean, I tried to give as many talks as I could. So when I went to a conference, if there was a possibility, I always chose to give a contributed talk, and that way get in contact with more people, show what I had done, and hopefully someone was interested in that. Also for me, I mean, if it is possible, sometimes for family reasons it might not be, but I mean, moving a bit around, getting exposed to other ideas, I think that's also really key for advancing your career. So that's from my perspective, and what helped me in my career. And then there was also one question we were asked to answer, what I would like to have known earlier. So this is more about my second part of my career. So for instance, I mean, what I experienced when I then suddenly became a professor, that there are differences in the behavior of women and men in professional environments, for instance, in committee meetings and so on. And I wish, I mean, I would have had maybe a training, like maybe coaching before. I mean, then certainly, I mean, you learn on the job and learn how to handle this. But I know from a relative of mine who made a career in industry that they have coachings for women who are approaching leading positions, specifically on questions like that. So that I would wish maybe also for academia, and that's maybe one thing. which I would like to have known earlier. So this is about a bit about myself and what I think helped me in my career, and I'm certainly happy to also answer questions on that later on. So, but let's now continue with science, and I would like to very briefly review with you theoretical foundations of deep learning. First, the broad picture, and then we will delve more into the area of generalization. I mean, some things you have heard now many times, so let me maybe just very briefly go through that. A neural network in general is a concatenation of affine linear maps and nonlinear activation functions. So you have the affine linear maps, you will denote them in this way, which mimic these connections between neural networks and the bias vectors, and then you have a nonlinearity applied to each neuron, and then you continue, and the nonlinearity is applied confounded-wise here. And certainly of key importance is, for instance, the number of layers of the network, the width of the network, and aspects of that type. Then we will later on study graph convolutional neural networks. So if you go to convolutional neural networks, now the affine linear maps, so there you have convolutions, again you have activation functions, you have another pooling layer to again reduce the size of the data, and so on. So that's basically what now happens in each layer. So in addition to what I showed you on the previous slide, you have now this pooling layer. We will go in a bit more detail later on, or if you have, let's say, a large matrix, you do subsampling to reduce it again to a smaller size. Now, what are the key directions in the theory of deep neural networks? For that, let's again briefly go through the main steps of how you apply neural networks. So typically, you have a function you want to approximate, maybe defined on a lower dimension manifold. It's usually a classification function, which we aim for. So for instance, you would like to separate cats from dogs. So then this area would be mapped to the value 1 and this area to the value 2. And what you have at hand are sample values, xi, f of xi, and these samples you now split into a training and a test data set. Then the next question, and that is already a big question, which architecture to choose. So how many layers to take, how many neurons in each layer, which activation function you would like to have not a fully connected network, because that's usually difficult for training. So you would like to drop some of the connections already early on. So after you've selected the architecture, you optimize, you train the neural network, and what you do then there is you learn the affine linear maps by solving an optimization problem. And what you aim for is that the neural network which you want to learn applied to xi is close to f of xi, which you know. And the closeness is given by a loss function. Maybe you also would like to regularize, so to impose additional conditions on these weight matrices and on the bias vectors like sparsity. When you solve the optimization problem, typically using stochastic gradient descent, and we learned yesterday from Rachel a lot about this algorithm. And once you've done that, you hope that the network you learned is close to your function f, and the closeness you now check by using the test data. And from this, I think, from my viewpoint, the key directions arise. There is the first question, which deals with the architecture. So that's also what Ingrid talked about yesterday. Expressivity. How powerful is a network architecture? Can it represent the correct functions? Can we give practitioners guidelines on how to choose an architecture in maybe an optimal way? So this requires certain areas from mathematics to tackle those questions. Yeah, so here the hope is to, in a way, it's the search for the optimal architecture for a particular application. It's certainly closely connected to also the learning procedure, where you ask questions like, why does the current learning algorithm produce anything reasonable? Although the problem is highly non-convex, why does it converge? And again, I mean, a certain set of methods which are used for tackling those issues. And then the area of generalization, which asks the question, I train my neural network on my training data set. Why does it perform that well on unseen data? And also which impact has the depth of a network. And so this is in particular learning theory, statistics, areas of that type. And if you view a deep learning problem as a statistical learning problem, then these are exactly the three areas you need to tackle: the approximation error from the hypothesis class, the error from the algorithm itself, so the optimization error, and the out of sample error, because you just train your neural network on sample values. And then from my viewpoint, I mean, there is another area which I find very exciting, which happens basically afterwards. After you've trained the neural network, you can then ask, how does the neural network reach certain decisions? I mean, if certainly these questions are very well answered, you have an extreme control about what happens during the training process, then, I mean, when you get a neural network, you don't need to expose it to that area, because then you have complete knowledge. But I mean, even if you have solved all questions here, still it could be that a colleague gives you this neural network and maybe you trust the colleague. So then you want to ask, how did this network reach its decision? Yeah, so which components are most important for contributing to that? And also there are a set of different areas which contribute. Yeah, so maybe let me also say this area is, I think, the most developed so far. There are very interesting results. I mean, saw some yesterday, classical results like universal approximation theory. This area is less developed. Also, there are now exciting directions. We saw also some yesterday. This is maybe the least developed area, the generalization ability of neural networks, also why neural networks don't overfit. I mean, it's still a mystery. And this area of explainability, interpretability, I mean, barely has any mathematics in it yet. I mean, there are some approaches using, for instance, information theory, but still, I think a thorough theoretical foundation has not even, I mean, has maybe slowly started, but I mean, there's a wide open field. Yeah, so generalization, I mean, already said, in particular in the high-dimensional, highly overparameterized regime, neural networks perform that well on the test data set. So they have a small difference between the training and the test performance, which is not completely understood at this point. I mean, there could be some intuitive reasons one could think of, whether it's a matter of the architecture, whether it's a matter of the training. But in fact, I mean, all of those seem to not come close to unravel this mystery. Very famous in this respect is what's called now the double descent curve, and that explains in some sense the phenomena, not explains, it shows the phenomena which we observe. So maybe if one looks at the left-hand side, so what you see here is basically the size of the neural network, so the capacity of the hypothesis class. If you view it from a statistical viewpoint, then you have here the error. And what you see here, this dotted line is the training error, the training risk. And certainly, I mean, as you enlarge the neural network, it will usually go down, because then, I mean, it can fit the training data very well. The test error is a different ballgame. The test error here also first goes down, but then after some point it goes up. And the reason is that the network, or here the hypothesis class, starts to overfit. And so this phenomena you see here, if for instance you would like to classify two classes and your classifier is not expressive enough or doesn't have enough flexibility, maybe you can just only separate it with lines, and you see that's by far not the best you can do with this data. If you have a bit more flexibility, maybe you do something like this, you get something like this after your training. But if you have too much flexibility, and if you have a highly over-characterized model, something like this could happen, which, I mean, seem to be not the best for fitting the data. And so this is overfitting, and that's why this error again goes up. But surprisingly, in neural networks, what one often observes is that after some point, the test error again goes down. And so this is called this double descent phenomenon. Whereas this is explained by statistical learning theory, this is not. And there are classical methods like BC dimension, Rademacher complexity, now newer uniform stability, or also neural attention kernel, which all try to understand this phenomenon. And there's a long list of contributors in that range. Now, what I would like to do with you now is I would like to take you to the world of graph convolutional neural networks. That's a much richer world. One can view normal neural network, normal convolutional neural network also as a special case. And because it's richer, also the question of generalization is richer. And so there's one aspect of generalization which we studied and where we could, I think, maybe get some interesting results, which I would like to show you. And so these are my collaborators on that project. Ron Levy, who's a brilliant postdoc in my group. Sohia Maskai, who's a PhD student in my group. Then Wei Huang and Lorenzo Bucci, both from Switzerland, and Michael Bronstein from Imperial College in London. And I think he's certainly extremely well known. Yeah, so graph convolutional networks, as I said, I mean, they're generalized classical convolutional networks now, and we can apply them to signals over graph domains. So graph signal is, you have your graph with nodes, we'll go into more detail in a moment, and then you map each node to a vector, let's say in RC. And as a convolutional neural network, also a graph convolutional network is, in each layer consists of convolution, activation, pooling, and so on. And these networks are extremely popular these days because there are widespread applications where you actually need this type of neural networks. There are recommender systems. This is recommender systems in customer satisfactory. So if you have customers and they rated maybe movies and you would like to know which other movies to suggest to them, you can use these techniques. Fake news detection, autochemistry, you see a molecule looks like a graph, and so you apply these techniques also to this type of applications. Now, what is the aspect of generalization I would like to study here? As we said before, generalization asks the question, I have my training data set, and I train my neural network on it, and then I hope that it generalizes to data which was not in the training data set, in particular that which is in the test data. And here, so we ask for generalization to signals on graphs. But now we have one special situation, because it could be that two graphs model the same phenomenon. Yeah, so let's say, for instance, you have a continuous space and you have two graphs which are discretizations of it. Then they model to some extent the same phenomena. So what you then hope is certainly that the neural network, graph convolutional network, has the same repercussion on both graphs, so has approximately the same output if you take this as an input. Yeah, so it could happen that maybe this graph is in your training set, but this is not. And so you see it's one aspect of generalization. So you study those, let's say, classes of graphs which mimic the same phenomena, and then you ask the question, now if some of that, maybe one of this is in your training data set, and you train your neural network accordingly, what happens to the others, which are maybe not in the training data set, but which mimics the same phenomena? So can you at least prove that the network generalizes also to those? And so this is an aspect which you don't observe in the Euclidean setting, but only here in the graph setting. And so what we show, and so this is sometimes called transferability, not to confuse this with other notions of transferability. So this is what we refer to, transferability, transferring to other graphs which mimic the same phenomena. And we we will show this for spectral graph filters and graph convolutional neural networks. So let's come back a bit more to the details, how a graph convolutional network is set up. I mean, activation function, this is trivial, you just apply it node-wise. Pooling is usually done, for instance, by coarsening. So you have a graph and then you fuse certain nodes to get a coarsened graph, and then you continue with this. The big question is what convolutions? How do you encode this? And so there are basically two approaches to convolutions on graphs. One is a spatial approach, the other is a spectral approach. So the spatial approach is basically directly extended from the Euclidean setting. Yeah, so you have basically a mask or a filter, which you slide here across the Euclidean plane or here across the graph. And what it each time does is it aggregates feature information from the neighbors of each node. So that's, I think, not very intuitive. But then there's also the spectral approach, which uses the convolution theorem. It's defined in the frequency domain, and so there the filters are then multiplied in our frequency domain. And there was for a long time the reason that spectral graph convolutional networks are not that good, and in particular also don't exhibit transferability. And we could show that this is actually not true. In fact, spectral graph convolutional networks are extremely effective also on that task. But you have to set them up the right way. So let's talk a bit about how we set that up. Yeah, I think everybody knows what graph theory is. So you have some vertices, you have edges between them, you have an adjacency matrix, and then you also have a degree matrix, which aggregates the weights from the neighboring edges. Using this, we can define a graph Laplacian. So we have a normalized version, which is the degree matrix minus the weight matrix, and then you can also normalize it. So that's an operator, it's a self-adjoint operator, and the eigenvalues are typically referred to frequencies, the eigenvectors, free modes. And if you look at, for instance, here in this little example, the graph Laplacian eigenvectors, you see that it's very much adapted to the geometry of the graph. I mean, not that surprising. So here you see low frequencies between those dumped shells in some sense, and higher frequencies. And so in the Euclidean setting, I mean, you have the Laplacian, like we all know, and the eigenvectors here are exponentials, and the eigenvalues, the frequencies. So that's the special case of the Euclidean setting. Now we need to ask ourselves, how do we define convolution? And the classical way to do that would be, I have my graph Laplacian, which I compute. I compute the eigenvectors of it, and then I define my operator in this way. So that's spectral decomposition. So you have your f, you have here the eigen vectors, and these would be your filter coefficients. So that seems quite straightforward, but I mean, there are certain problems with this approach, because first of all, I mean, you have to compute the eigen decomposition, which is, if you have a huge graph, I mean, very slow. And also, usually there's no fast Fourier transform for graphs. So that's already a huge obstacle. But then, I mean, even worse, if you do it that way, I mean, then this will not be stable, for instance, for a graph just perturbations. Because if you perturb a graph, I mean, these eigenvectors can change rapidly and significantly. So even if you have a graph and you just slightly perturb it, the action of this convolution operator could change drastically. So with this approach, you don't have a hope to get transferability. So one needs to think of something else. And what one can do is one can think back of your functional analysis class, usually course number 2, which is about functional calculus. And functional calculus, not, I mean, if you're not that familiar, not to scare you, what it basically does is the following. So we have our operator, and so this is the classical spectral decomposition of an operator. And this functional calculus now tells us something very interesting. It tells us I can apply functions to operators. Yeah, so let's assume I have a function. Let's assume it's the square function, which might be. Yeah, so if I have a square function, certainly I can take this. I can apply it to an operator. But functional calculus allows us to apply, for instance, any continuous function to an operator and get then a meaningful action of the operator. And you see here, if you do that, I mean, your decomposition looks like this. So then, I mean, the G in here in this decomposition is applied to the eigenvalue. Yeah, so if you are not familiar with functional calculus, I mean, what you should take from this is I have operators, the Laplacian operator, for instance. Now I can apply functions to it. And so this is the formula I get. And for instance, in the special case that my G is a rational function, I can even exactly write down how this operator looks like. Yeah, I just plug it in. And so this gives then a meaningful definition. Also, it's a whole theory of functional calculus. I just make it sound maybe so easy. I mean, but so this is the essence. Now, how can we use this to our advantage? What I now do is, yeah, remember this was our previous definition. So now I take my graph Laplacian, and my filter is now not a sequence of discrete values, but a function. My filter is a function, and this function I now apply to my graph Laplacian. And so then we saw on the previous slide, this is what I get on the right-hand side. And that's, so remember, that's now the difference. Here, my filters are coefficients, but here it's a function, and I then apply it to the graph Laplacian, and this gives me my convolution operator. And so this solves the instability problem, because now you see here we had the problem that if you perturb, then these eigenvectors might change a lot. But since these stay fixed, this operator changes a lot. But here you have a counterbalance factor, because, well, the eigenvectors might change a lot, but then also, I mean, these eigenvalues will change accordingly and counterbalance that to some extent, so that you can still prove then stability. And also it solves the computational problem, because we saw on the previous slide, if my G is a rational function, so if I go back, I can write down exactly how the operator looks like. Yeah, I don't need to go through the eigendecomposition necessarily. So that's the second advantage. So spectral filtering using functional calculus is in some way the way to go for spectral graph convolutional neural networks. And that's also now widely used. Okay, so let's come back to our problem of transferability. Again, let's recall what we want to do. We want to analyze if I have two graphs which model the same phenomena. And I have this graph convolutional network, which is fixed and which is maybe being trained on one of those graphs. I would like to analyze how it performs on the other graph, and maybe even get an error bound. But I mean, the question is certainly, what do I mean by same phenomena? And I mean, here I was a bit hand waving. I explained we can have something maybe continuous from which you sample. So there are basically three different models which you can take. The first is looking just at perturbations, which is maybe the most restricted one. You have maybe two graphs, and one is a small perturbation of the other, and that you view as mimic in the same phenomena. Or you have, which maybe the previous picture a bit indicated, you have something like a topological space. You sample from it, and then these are the two graphs you then say mimic the same phenomena, because they are sampling from the same overlying continuous space. And there's another approach, the graphone approach. So graphone is some sense a continuous object of graphs, And then you can take two graphs which come from the same sequence converging to this graphome. And we will now discuss a bit more detailed this, and then we'll see how, if time permits, maybe I'll also say a few words about the graphome approach. Okay, so let's look at the sampling procedure now. So if I have a weighted graph, I can view this as I have points and I have a strength of correspondence between those points, which is given by the weight. And then if we, let's say, for instance, take a metric space, I also have points and I have a distance between those points. So now I can view it in the following way. If my distance goes up, then the weight goes down. Yeah, so this will be the correspondence between, let's say, the distance and the weight. And so then I can sample this metric space. I can get the weights from the distances in this way. And so this gives me then a notion of a graph representing the same phenomenon. Okay. So let's see what we want to do. So these two graphs now come from the same metric space, let's say, and I put a continuous signal on that, on the metric. So I have now on my metric space, which is where both of these graphs come from, I have some signal, some function. Okay, so now I would like to compare the repercussion of a filter on those two graphs using this functional calculus. Okay, so what do I need to do? First, I need to bring the continuous object, the signal down on the two graphs. Yeah, so I sample it. This is fairly straightforward. So this I call G1 and this I call G2. And so I brought it down on both graphs. Now I need to apply the filter. And remember, our filter is a function which I apply to the graph Laplacian. And so that way I can also now adapt it to these two different graphs. I have my filter, G, and I apply it here to the graph Laplacian coming from this graph, which I call λ1. And here from the other graph. So I have the same filter, but adjusted to the two different graphs. And then I bring it up again. And now I can compare it in the continuous world. Yeah, so I bring it down on the graph, I apply my filters, I bring it up again, and now I compare. And this arrow gives me the repercussion. Okay, so this was the nutshell. This is the essence, basically, of what I now do in a bit more generality. Yeah, so now, we have our analog, our continuous domain. So this is, for instance, a Borel space with a continuous Laplacian. I have my digital world where I have graphs with graph Laplacian. I have Palevina spaces on M, which are band-limited spaces according to this graph Laplacian. I have my sampling operators, which bring things down from these Palevina spaces defined on M to the world of my discrete world, so R2 of G. And then I have an interpolation operator which brings it again back up. Again, what I did on the previous slide, just now a bit more general. So you can call it, it's a digital signal processing framework. Okay, so now, in our error estimate, these three components will appear. The first is the transferability error of a filter. So here I call the filter F. Sorry about that. It was S before, G before. Yeah, so I have now my signal. I bring it down on the graph, I filter it, I bring it back up, and I compare it to if I don't leave the continuous world. So that's one part. So I compare the discrete world now to if I just had stayed in the continuous world. And that way later on I can compare the repercussion on two different graphs. Then I can look at the transferability error of the Laplacian. So here my filter is just the identity. So that gives me this error. And then I also have the consistency error, which just studies if I bring things down on the graph and I bring it back up, what error do I make? So there's no filter involved here. It's just the sampling. And so what we could prove, this is the first result, and it looks, I mean, a lot, but maybe let's just look at the essence here. What this says is, I mean, according to the three errors I showed you, that the transferability error of the filter is bounded by the transferability error of the Laplacian and the consistency error. Yeah, and so this is spelled out here. This is the transferability error of the filter. You see, you bring it on the graph, you apply the filter, you bring it back up, you compare it to the continuous world. This is the transferability error of the Laplacian. You see the filter which is applied here is just the identity. You see here the M comes into play, the C and the D. These are these constants. And then here you have the consistency error. And so this is in the operator norm, and this is if you apply it to one vector. So this is half of the answer. I mean, at least part of the answer. Yeah, you compare one filter, the percussion of one filter, with the continuous world. And let me already say at this point that this is a very flexible result. I mean, there are a lot of special cases which you can apply it to. You can apply it to, let's say, M is your Borel space, G is a sampled graph, and then the bringing down and bringing back up is sampling interpolation. It could be also that M is a fine graph and G is just a coarsened graph. Then, I mean, you have according sampling and interpolation procedures, or M could be a graph and G could also be a perturbed graph. And then these are the identities. But then, I mean, what you certainly would like, and so this is the full result now, is that if you have a graph convolutional network, you have here two graphs, you pass it through, and you would like to compute the error in the end. And so this is yeah, so you have these two graphs, you have the two Laplacians, you have your Laplacian on your continuous space, you have a graph convolutional network with ReLU filters, and you have these two hypotheses, and you might recognize them. This is the consistency error. This is the transferability error of the Laplacian, which appeared in our estimate before. So now you assume that they are bounded by delta. And so this is the full error. If you now pass one graph through the neural network and then the other graph, and so this is the bound which you obtain. You see the components here. This is the delta from here. This is the number of layers again here, and this is the dimension of the Pauli-Wiener space. Yeah, so you get a very precise error bound that way. And so now seeing this, you can say, well, I mean, the consistency error, so these are normal errors. And then, I mean, if you have an error bound, you certainly want to control the error. The consistency error, well, you can control by how dense the sample and things like that. The transferability of the Laplacian is not that clear, whether you can control it indeed. And so the question is it reasonable to assume that the transferability error of the Laplacian is also small? And there, I mean, let me just state an informal result. One can show that if you have your, let's say, continuous space, and you sample randomly, then those graph Laplacians approximate the continuous Laplacian with very high probability. So in that sense, I mean, you can say transferability, so this error is small in high probability. So this is, let's say, one result analyzing the transferability of the Laplacian and therefore bounding then the complete error. Okay, so the graphone approach, let me briefly go through it because then I would like to also show you some numerical results in the end. So a graphone, as I said, is a limit object. Graphone is just a symmetric measurable function on the unit square to 0, 1. And it can be understood in this way if you, yeah, so you, for instance, with this way, you can randomly generate graphs. So if for each vertex of your graph, you have a random value, then you would plot the edge with the probability given by this graphone. So that way, if you have a graphone, you can get a lot of samples that way. But maybe more intuitive would be if you, for instance, have a graph, you have an adjacency matrix, you can construct a graphone very easily by just this piecewise linear or piecewise constant object. Yeah, so this is, for instance, also a graphone. Yeah, but in that sense, I mean, you can, and also maybe this is maybe also from an intuitive viewpoint a bit enlightening. If you have a graph like this would be your adjacency matrix, and then the graphone would be a limit, so would be the function, this function on the square. If you would have a random graph, the adjacency matrix would look like this, and then the associated graphone would look like this, because every edge is plotted in some sense with the same probability. So because it's a lot technical, I don't want to go too much into details there. So let me just say, I mean, graphones can be understood as limit objects of graphs in this way. And so therefore, you can also phrase the notion of convergence, a sequence of graphs to a graphone in a particular way. You have yeah, let me, because time is a bit ahead, let me not go too much into the details. Let me say, I mean, there is the convergence definition, sequence of graphs converging to a graphone, and also associated, you have, let's say, a functional analytic framework, so that you can also define according functional calculus field. So, and then, I mean, via this framework, you can actually prove, for instance, the following: if you have a sequence of graphs which converge to such a graphone in this way, like one defines convergence with homomorphism density, and then I have a filter, so a continuous function. Then I find a sequence of perturbations of these graphs, so that if I now apply the continuous function to these operators, so these operators are these Hilbert-Schmidt operators now, which you can to some extent compare to the Laplacian which we had before, then you also have conversions. So in that sense, you can also prove results that the filters applied to these elements of your sequence towards the graphone also converge to the limit object. Now, and so then you can extend that and get, in a certain sense, similar results as we saw before. But it's, yeah, it's much more involved and would take more time than I have to explain it in detail. But I hope you got a bit of the flavor of these types of things. So let me now briefly say something about numerical results. You can view, if you think about transferability aspects, you can view it in two different ways. First of all, such a graph convolutional network can have concept-based transferability. Yeah, so that would correspond to, I expose the convolutional neural network to, let's say, a lot of different types of graphs mimicking the same phenomena. Then the network will already learn how to transfer. The other is principal transferability. I expose the network just to one example of this phenomena, and then I hope that there is a built-in capability of graph convolutional networks to then transfer what I learned from that one graph to all the other graphs which are in the same class. But in some sense, I mean, the success of spectral graph convolutional networks relies on both types of transferability. So what you see here is a comparison between spatial graph convolutional networks and spectral graph convolutional networks. The application here is that you have a continuous image which you sample with different resolutions. And what you see here, the blue, this is the spectral graph convolutional network. So the accuracy for different image resolutions decays much slower than for the spatial graph convolutional network. So this shows, I mean, spectral graph convolutional networks seem to have a strong transferability property. What you see here are examples comparing the Laplacian error with the filter error. We saw from the bound that there should be a somehow linear relationship if this bound is tight. And here you see also this linear relationship. Here you see so this is about this example of perturbation, just randomly removing edges and then looking at whether this the graph convolution network has the same repercussion. Yeah, randomly adding edges, randomly removing vertices, all of those are basically linear relationships. And then what was very interesting to us was there was a paper by Nielsen and Bresson in 2020 where they studied these functional calculus graph convolutional networks on various different tasks, applying various different rules. And what they found out is that indeed these type of networks, so spectral graph convolutional networks coming from functional calculus, are indeed at least as good as other state-of-the-art algorithms, in particular those spatial ones. And in some sense, you see it's even better than that. So this shows, I mean, this is definitely a way to go, because here you then also have rigorous transferability results. Okay, so let me conclude. I think graph convolutional networks, I mean, it's an exciting topic, in particular concerning generalization. There are aspects, let's say partial questions, which I showed you here, the answer for one of that, when you have graphs modeling the same phenomena. We showed that indeed spectral graph convolutional networks can be set up in a reasonable way using functional calculus. And indeed, they can be shown to exhibit transferability. Then this was the bound we then derived finally. So in that sense, I mean, one part of the generalization question or mystery of graph convolutional networks is maybe now a little bit revealed, but there are certainly various other questions still remaining. And with this, I'd like to conclude, and thanks a lot for your attention.
Thanks a lot, Gitta, for this interesting talk about graph convolutional neural networks. So yes, we have time for 5 minutes for questions. Should we start with the audience that is physically present in at the Institute?
Let's start with the online audience. I think there is a moment.
Okay. So you can type your questions or you can just unmute yourself and ask a question. All right, so if there's no question, no, there is, so Martin Benning wants to ask a question, please go ahead.
Yeah, hi, thank you, Gitta, for a very nice talk. I hope you can hear me.
Oh, yeah.
Yes, I was wondering, because the last example you showed with the different resolutions for the images, there are obviously also approaches for networks to try to make regular convolutional kernels, for instance, scale invariant. Could this be basically, I mean, can both approaches maybe somehow, is there some, let's say, some analogy between the two? That maybe there's some, I mean, it seems to me, obviously, you are, well, it was just one example, and I guess yours is more general, but is this sort of the idea of invariance that you somehow exploit in this regard?
Yeah, I think that's actually an excellent comment. Yeah, I think so certainly, yeah. So as you said, I mean, this is more general, and this was just one example, but yeah, you can view it in that way that the filter is, for this application, scale invariant, and so then the bound, the error which we give, could be also used as an error for that.
Mm-hmm. Yeah, thank you. Thank you.
Okay, any other questions? So maybe I have one, Gitta. So you, this is at the very beginning where you talked about this double descent curve, which I find interesting. So I mean, is there then, I mean, does that mean that you should go for the very overparameterized regime because the test error will go down again? And what are the limitations?
I mean,
or what is
also if you talk with practitioners who train, I mean, extensive neural networks, I mean, some even tell you, well, I mean, take that neural network which still fits in your GPU. So I think that's, yeah, so that's usually the guideline for setting up. I mean, certainly often one can get away with smaller networks, but larger is usually better.
And has this phenomenon also been seen for or tested for these graph convolutional neural networks that you've talked about?
Yeah, so also graph, I mean, so maybe let me also. Yeah, I mean, yeah, to some extent, this has also been analyzed there. I think the techniques which is usually used right now, or one of the most common techniques, are the attention kernels, and so there are also works now using these for analyzing generalization ability of graph convolutional networks. Yeah, so that goes a bit hand in hand.
Well, thanks a lot. So I asked the audience one more time. So we have 1 more minute if there's a question. Either for the physically present or the online audience.
Maybe a quick question. Yeah. First of all, thank you very much for the nice presentation. So a quick question is, can you elaborate a little more about your question of how is the extent or reasonable to assume that actually the error of the Laplacians is always fulfilled, or in other words, your right side of your inequality is always going to be fulfilled, because that is going to depend on how you treat actually your data, right, or your sampling.
Yeah, sure. Okay, so if I understood your question correctly, you were wondering, I mean, how you can, I mean, and to which extent you can control it.
Yeah.
Yeah. So the consistency,
yeah.
The error definitely depends on the data. So there.
But there is no guarantee, right, that is going to always fulfill, but only depends on how you treat the data, particularly for the error of the transferability of the Laplacian, right? Yeah,
because I mean, if you, let's say you have real world data and then you would like to apply this error bound, I mean, you would first need to wonder what is the unit space and so on. I mean, so in that sense, I mean, going that way from real world data to computing this explicitly, I mean, requires for this consistency error would require to have a model for, let's say, a continuous space where this comes from. And then the question is certainly, I mean, how dense do you sample? And that way it's difficult to control that. But I mean, in principle, for instance, for, let's say, this imaging application there, I mean, you can assume you have, let's say, a continuous image, and then you have control over that in that respect, but that depends very much on the data.
Thank you.
All right, with that,